Hi, everyone. 1 minute more. Seeing more people joining. Okay. Hi, everyone. Welcome to Wasmer Things, an upside-down guide to WebAssembly. So, I don't know if you've ever joined one of those sessions where the speaker have these slides where they've copy-pasted text from a web page, and there's terrible clip arts, horrible animations, overstretched graphics, terrible fonts, and they have a screenshot of the web page and saying, oh yeah, you can download the compiler for WebAssembly from this website, and my favorite download website is 2Cows, and then you can write your C program, and then you compile it, and then, sorry, this is my first day. Let me reboot the computer. It's my first time. So, and then you can see it's compiled and it prints hello world to the screen. So when you attend one of those sessions, you don't really learn a lot. It's something that you could learn yourself from a website, from a tutorial. So, and it doesn't give you enough depth, in my opinion, at least. I mean, it just gives you an overview of how it works, and it doesn't give you how it actually works. It's kind of like saying, here's the basics, and then get to do the whole thing yourself. So I want to take a different approach myself today. So welcome again. A couple of words about me. My name is Edoardo Vacchi. That's my handle pretty much everywhere on the web. Yeah, I did research at University of Milan on DSL programming languages. Then I joined a research development group at Unicredit when I did a little bit of that and did a bit of something else. Then I work at Red Hat. Some of my colleagues are here today, ex-colleagues, unfortunately, because I joined another company very recently, and I'm working on a WebAssembly runtime called Wasm. Check it out if you don't know it. Yeah, since we don't really know what the Bluebird is going to end up doing, this is also my Mastodon address if you'd like. And enough with the bullshit. Let's start with the actual content. So I assume that a lot of people here are familiar with the JVM, so I'm going to take an approach, and I'm going to take that kind of perspective. I'm going to talk about what's the difference between WebAssembly and JVM, because on a first glance, a lot of people that are familiar with the JVM may say, well, bytecode in the browser, I mean, we had Applets already. What's new with that? So in order to understand that, I want to tell you the history of WebAssembly, which I should rather say it's the history of running arbitrary code in the browser. So in order to give you a historical period, let me give you an idea through a series of screenshots. This is Netscape 6. This is Mozilla 1.0. This is Internet Explorer already on the 6th version, that we love, the 6th version. So at that time, by the way, I didn't install a VM just to run those. There's a website where you can download all these screenshots if you're feeling like vintage. At that time, we already had JavaScript, and you could write JavaScript code to run in your browser, but it wasn't really used to write complex applications. As you probably remember, it was mostly used to do rollovers and graphics and adding a little bit of spice to your website. If you wanted to do proper interactivity, what you really wanted to use were plugins. So plugins were a bit of native code that would plug into your browser, would link against it, run at the same privilege level, and it could deliver you with capabilities that the browser at the time couldn't deliver. So multimedia capabilities, music, videos, or even programmability. So you had platforms, of course, Java, so to run Java applets. Then at some point it was Silverlight. Before that, there was Flash and Shockwave. A lot of stuff that actually today is basically deprecated, but at the time, and of course, well, some other crap to browse your intranet for some reason. So using plugins had the benefit that it could allow you to do something that the browser could not natively deliver at the time, but it came with a lot of downsides. First of all, your users had to download the plugin themselves, and they had to keep it up to date. another thing that I already mentioned, these bits of code, arbitrary code, had to link against your browser, and your browser ran on a specific operating system, which ran on on a specific architecture. So the compatibility matrix was kind of complex. So if you wanted to deliver a plugin, you had to deliver it for all the architectures, operating systems, and browsers you wanted to support. And on top of that, you had to deliver security fixes, otherwise that could be an attack vector. So besides writing a plugin wasn't really something easy for everyone. So yeah, it came with a lot of downsides. Okay, so what about using JavaScript itself? So at some point, people realized that JavaScript was not that ugly a language. You could actually do interesting stuff with that. I'm not going to talk specifically about that, but I'm going to jump a little bit further in the future, around the late 2000s and beginning of 2010s, when people start to use JavaScript as a compilation target. And I guess Federico later will tell you something more about transpilers as well. I'm going to use that just as a bridge to go further in the discussion. But what I want to say is that basically there were quite a few languages, CoffeeScript first among the mainstream languages, that specifically targeted JavaScript as a compilation target. There were other. Dart, which now is a transpiler for JavaScript, at the beginning had their own VM, and it also did transpilation. TypeScript, it's probably the most beloved language of that series there. AppScript was folded inside TypeScript, and at the beginning was an experiment, all still by Google. And Bubble.js, you probably know, because it's a transpiler that allows you, while the other are kind of different languages, at the very least extensions to JavaScript, like TypeScript, Bubble.js basically allowed you to write using a later version of JavaScript and then translate that into an older version so that you could run it on any browser, even if it didn't support the latest and greatest. And besides, there are many others that I'm not mentioning explicitly, but I want to mention just a few. Like React at the very beginning, now I think that's deprecated, but they had extensions for JavaScript to support XML literals, and ClojureScript, Scala.js, and of course, I want to give a special mention to Gwt, because I think it was one of the first to provide a compilation toolchain from Java to JavaScript. And I wanted, and of course, mscript, which I mentioned at the beginning, we're going to mention today again. By the way, remember Gwt, it still exists. Now it's called J2CL or Jekyll. And it's still used, so if you're interested. So, but what I wanted, the point that I was trying to make is that at that point, in these years, as web developers start to accept as a fact of life, as a common part of their workflow, that you may have to compile your language into something else, into another language, into a compilation target, which is not natural because JavaScript is a dynamic language which you usually just run. You just write and run. So this friction became just part of life. And that's very important. Because it brings us to NECL. NECL was a technology that was embedded in a Chrome browser to run arbitrary code, binary code, that allowed you, it was a tool chain that allowed you, well, first of all, it was a tool chain that allowed you to compile C and C++ into a restricted form of a native executable, a restricted subset of instruction set for CPUs. There were several CPUs supported, and then there was a variation of that was called PNACL. There was a portable subset. So basically, there was kind of a VM inside your browser that interpreted that subset and compiled it on the fly into efficient code for your target platform. This kind of may kind of sound like plugins, but it's not the same because while plugins you had to deliver like through download website, you had to download them. You could deliver your binary payload, NECL payload, directly from your website. So the browser will download it automatically and run it. So way more seamless experience, more similar to what you expect when you're just running JavaScript. You don't have to download extra code. The browser does it for you. So this was, however, specific to the Chrome browser, and at some point it was deprecated. Why? Well, one of the reasons was ISM.js. Same years, more or less, 2013, the word, as you see, so the transition from C++, we compile to a specific target that allows us to run code in a browser. So since you're compiling, and since you are already in the mood, you already have this idea that you may target JavaScript as a compilation target, what about compiling C and C++ into JavaScript? And this was the goal for the mscript and toolchain at the beginning. Now the mscript and toolchain actually supports WebAssembly as well. We'll get to that. But the idea was that you could define a JavaScript subset with specific features, with a specific look, basically, so that it could be optimized by your regular JavaScript runtime. This is an example. Don't focus too much on it, but the idea is that you have this snippet of C code at the top where you see there are types. There is integer types as argument and return type. You don't have types, explicit typing in JavaScript, but by using this syntax, by putting it into a bitwise OR, this I variable, this operation has only meaning if I is an integer. You know that JavaScript doesn't have explicit integer types. It's only floating point. But this operation only makes sense if I is an actual integer. And this basically, it's a way to express in a syntax-compatible way with JavaScript that what you're running needs to be managed differently. And so basically, by doing this, they were able to support a JavaScript subset that could be optimized and interpreted in an efficient way. The groundbreaking Unreal demo, Epic Unreal demo by Mozilla showed the capabilities of this kind of technology, this POC. So the Epic Citadel demo. As you can see here, we have a fluid 3D scenes, fluid 3D scenes with the camera moving, with reflections, lighting effects, with performance, with the fluidity that comparable to native code. So it really showed, and this was the Firefox browser with the SpiderMonkey engine, nothing else. It was just tuned to support this JavaScript dialect. Now, you may say, well, that's fancy, that's nice, but what you're showing here is just could be just a pre-rendered script because there's no gameplay, there's no interactivity. Well, you would be, that's a good point, but actually, there's also gameplay. So you could also do interactive gameplay with this, and this is, I think it's an Unreal level. So this really proven that it was feasible for the browser with a set of technologies that the browser supported already, JavaScript and a JIT compiler for JavaScript, SpiderMonkey. You could support efficient JIT compilation of a very specific subset of JavaScript. So, what is WebAssembly? So WebAssembly is a portable compilation target, and I want to stress this is the key part of it. It's a portable compilation target that is meant to be interpreted in an efficient way by a virtual machine. It's not just a compilation target, it's a binary instruction format for a stack-based virtual machine. And the other key thing that makes it kind of different from Java applets is that the goal is not just to run on the client in a browser, but to be able to run both on the client and both on the server. And actually, server-side and backend, since I am a backend programmer myself, it's the part that is more interesting to me. I mean, definitely it's useful, it's fun, it's interesting, and opens a lot of possibilities to be able to write any language and target the browser, but it's exciting to have a VM that is truly polyglot. Now, again, we are probably biased here towards the JVM. So what's the difference with a JVM? Like, source code is compiled into bytecode. So same thing. It's stack-based, just like WebAssembly. You can run it on the client. You can run it on the server. same thing. The bytecode is interpreted and just compiled in native code, fast native code, efficient native code. So what's the difference? Well, on the surface, you may wonder, is history repeating? And on the surface, you may be right, but there's a but. So there's a quote from Solomon Hykes, who is one of the author, if not the main author of Docker. And this quote, it appears frequently when people talk about WebAssembly. If Wasm plus WASI existed in 2008, we wouldn't have need to create Docker. That's how important it is. WebAssembly on the server is the future of computing. The standardized system interface was the missing link. Let's hope WASI is up to the task. What the hell are you talking about, Solomon? What does Docker have to do with WebAssembly at all? Because Docker, you know, it's Linux containers, so it's a set of API, a set of syscalls to sandbox and virtualize an executable, a set of. So it's a sandbox technology, then there's packaging and delivering and distribution. What the hell does this have to do with WebAssembly? Well, we'll see that. There's another quote, which is in the same thread. Maybe JVM could have been the bigger, because sometimes someone said, well, what about the JVM, which is something that we're wondering ourselves. Maybe JVM could have been the biggest runtime for all applications, regardless of language, but the fact is it's not. Now Wasm is trying to solve the problem in a new way. It seems that they might pull it off. That's a good thing. It does not diminish the value of JVM at all. So what's the difference? Again, so why is Solomon saying that? So we saw this slide already. So what's new? I'm just repeating it. Source code, bytecode, stack-based VM, client-server, bytecode interpreted. So what's the difference? Oh, I wanted to mention this, which I recently discovered. This is not the first time that I do this presentation, but this is new. It's not new, literally. Like 2009, it's the last release of this tool. But just to make it clear that I'm not a fan of either technology, and just giving you information, someone actually tried to target the JVM with arbitrary code. In particular, this was a toolchain to allow you to run any C++ program, compile it into bytecode, and execute it on the JVM. So people tried doing that. But the reality is that Java bytecode was never really meant to be a general-purpose compilation target. And I have I have proofs. This is a paper, Bytecode's Meet Combinators Invoke Dynamic on the JVM by John Rose, when there's a specific line that I'm highlighting here in the abstract that says the JVM was designed for just one language, Java. And so when it is used to express programs in other source languages, there are often pain points. This paper was introducing to the word a new bytecode opcode, a new bytecode instruction called invoke dynamic. That instruction was specifically introduced to support dynamic languages such as Groovy, JRuby, Jython, and it shows that the JVM, wasn't really meant to run those languages, and it was for the first time acknowledging that people were trying to use it for that, but it didn't really fit. So the goal here is to find something that fits. There's LLVM. So you may say, what about LLVM? Can't we just use LLVM in a browser? LLVM project, this is from the website. The LLVM project is a collection of modular, reusable compiler and toolchain technologies. So as you know, you can use LLVM. It's the backend for the middle end probably for Clang, and so C compiler for Swift, and other programming languages. At some point, it was the backend for Rust. I think they switched to CraneLeaf now, but a number of programming languages are leveraging LLVM to compile to multiple targets, not to run it. In fact, they say on the website, despite its name, LLVM has little to do with traditional virtual machines. The name LLVM itself is not an acronym. It is the full name of the project. Unfortunately, that is bull, because if you browse to one of the very first papers on LLVM, they specifically spell out that LLVM meant low-level virtual machine. Now, they do say here that it has little to do with traditional virtual machines. And what they meant is that even though the name could have meant virtual machine, it's not really meant the bit code. They call it bit code. They have an intermediate representation, the bit code, that is meant to be. It is meant to be translated into multiple compilation target. So their bytecode, which is called bit code, it's only meant to be used to be retargeted, to be translated into another real-world architecture, like, I don't know, x86, ARM64, RISC-V. So it's not really meant for efficient interpretation execution. Just for you to know, this little bit of code that may seem hard to understand, it's not that hard to understand. As you can see at the top, there's a constant. I don't know if you can see it there at the end of the room, but there's a hello world string at the top. And then there's main that takes an argc, I32, an argv, and this already should ring a bell. This is actually the translation of a C program that prints called printf on hello world. So it's just an hello word that's translated to this LLM VMIR. And as you can see, even though it looks weird, it's actually pretty kind of readable. It's not that far away from the original C code, so it's kind of high level. Now, the point I was making is it was never really meant for efficient interpretation and execution. The tool chain at the oldest version came with an interpreter for LLVM IR, for the LLVM bitcode, but it was never fast. And I think they dropped that at some point. Now, someone in the audience may say, well, that is true, but what about GraalVM? Because GraalVM, as among his collection of features, by the way, if you're here, you're missing out because Alina's talk is very cool. But anyway, GraalVM supports running LLVM bitcode in an efficient way. In fact, that's the way they support, as far as I know, C Python extensions in their Python interpreter. So it is possible to run bitcode, LLVM bitcode in an efficient way, but again, this is a JVM-based technology, and as we saw, the JVM has other problems to be embeddable. So yeah. Okay, so what's the solution then? So we already have web browsers, and as we saw with the ASM.js demo, it is possible for these browsers, for the engines that run in those browsers, to run a specific subset of JavaScript in a very efficient way. How did we end up there? How do we end there? If you recall, JavaScript engines at the beginning weren't particularly efficient or fast. I think the ground was broken when Chrome was first released with the V8 interpreter engine compiler. So they demonstrated outside, they brought to the mainstream that JavaScript could be executed in an efficient, fast way, and I mean comparable to native speeds. So they've shown that JavaScript could be the kind of platform. So now we have basically all the pieces, kind of. We have a delivery platform, the browser. We have a fast engine, and we have shown that these engines are able to run some flavor of code, in our case, a JavaScript subset, that could be interpreted in a fast way. So the missing bit is just one, a proper compilation target that could be run by those browsers. So WebAssembly is just that. It's a compilation target that can run in the browser, or, to be more precise, that can leverage the engines that are usually inside the browser. But as we know, Node.js can be run outside the browser, and there are others as well. We'll see those. So we have all we need to have this new format. So that's what WebAssembly is. So the promise for WebAssembly is to be able to run any language in your browser, provided that there's a compiler for it. As you can see here, there's Rust, there's C++ and C through mscripten, there's Swift, because they're using, of course, the LLVM toolchain. There's Zig, there's AssemblyScript, And there's a number of other languages that one way or another are able to run in the browser. And the list is growing. I haven't put Java here, but there is some bit of support. If we have enough time, we'll talk about that too. Runtimes. Of course, I've mentioned V8. There's also Dino, which I think it's still based on V8. And this is from WebAssembly.org. And at the top, you can see compatibility for browsers and famous runtimes. The most widely used runtimes that are probably Wasmtime and Wasmer. And that's the reason the title of the talk is the Wasmer things. It's not just a pun. There's a runtime called Wasmer. And this compatibility matrix shows you what features are implemented in each of any of those. And as you can see, there are a lot of features that are not available, especially at the bottom, because those are in progress proposals. They are not finalized. So, yeah, the support is sporadic. Let's focus a little bit on binary instruction format that I mentioned for a stack-based virtual machine. In what way is this different from the JVM bytecode? So, first of all, yes, the JVM is a stack machine, but the WebAssembly machine, it's a structured stack machine. So there is a stack of values, but the control flow is structured. So while in the JVM you have jump instructions, arbitrary jump instructions, you can jump anywhere in the body of a method. In WebAssembly, you cannot do that. Okay, let's and it's a virtual instruction set architecture. Let's see an example of that. So it's structured. There's both a flat representation and a structural representation. So let's, for example, see a simple expression such as x plus 2 times 3. Okay, so let's say x is 4. Okay. So let's start at the right. So the first instruction says, I'm going to get the value 4x and put it on the stack. So x is 4. So on the stack now it's 4. Then I'm going to put on the stack the constant value 2. So on the stack there's 4 and 2. All right, then I'm going to call the add instruction. So add 4 and 2, which is 6. Yes, good. And then I'm gonna pop 4 and 2, and I'm gonna push on the stack 6. Now I'm gonna push on the stack 3, the constant instruction 3, the constant value 3. So on the stack now there's 6 and 3, and I'm gonna call the multiply instruction, which pops 6 and 3. 6 times 3 is good. So the result of the expression is 18. Now, even though the instruction on the right-hand side looks very different, let's try to do it again, interactively here, as if we were the interpreter for this bytecode representation. This is the nested representation. So parentheses are resolved in the way you expect. So we start from those that are innermost. So we get the value for x, which is 4. We get the value 2. So this expression evaluates to 4 and 2. And then outer expression is add. So you add 4 and 2, which is 6. And then the result of this expression is 6. And then you have the constant expression 3. So you have 6 and 3. And then the outermost expression is multiply 6 and 3, which gives you 18. So basically, what we have done on the right is the linearization that you see on the left. So these two representations that you can write, this is the so-called Wasm text format, or WAT. You can actually write this code, and they are completely equivalent because, as you saw, it's basically doing the same thing. It's just that the one on the right, it's a little bit more readable, even though for our non-Lisp trained eyes, it may be a bit less comfortable, but if you are familiar with that, it's pretty much scheme. And there's a reason for that, because if you know, I mean, there's a reason because it's convenient, but the other reason is kind of a hint at the history of JavaScript, because in its origins, it was supposed to be a scheme interpreter. Then Java was fancy and famous at the time. What about the structure control flow? Yeah, this is an example of Java bytecode. I won't go, well, just give it a glance. There's an if, there's an else. As you can see here, you can probably notice that there's an if and there's a goto. So this is unstructured control flow. You don't have blocks. You just jump to a particular index inside your bytecode. The structure control flow, on the other hand, does nest. So there's an if, there's an and, there's an else. So you cannot jump to arbitrary location inside your program, and that's for safety reasons. Even this is the nested representation. There's a linearized representation that, as you can see, it's completely equivalent. But the key point is that there's no unstructured control flow in WebAssembly. It's only structured control flow. So this makes it even further different from Java bytecode. And of course, the other thing that is important and interesting, which does not necessarily make it different from Java bytecode, but which makes it non-web specific despite the name, it's enabling deployment on the web for client and server application. So when you say web, you think client. It's not just that. Again, what the hell are you talking about, Solomon? Why is this an alternative to Docker? Well, as we say, Linux containers are for sandboxed packaging and distribution. So as for packaging and distribution, let's say that's another kind of problem. It's just a matter of having a server where you can download basically your payloads. That's it. What about sandboxing? What makes WebAssembly interesting that way? And so a very recent news is that Docker is also providing a WebAssembly engine now. Wow. What does that mean? Okay, let's. Solomon was mentioning the Vacchi technology. What's that? So Vacchi is the WebAssembly system interface. Basically, the idea is I would like to run WebAssembly outside the browser. So how can I do that? Well, normally what happens in the browser is that you have some bit of, you cannot probably read that, but there's usually a WebAssembly module, and then you have a bit of JavaScript glue code, and then the browser runs the JavaScript glue code, then runs the WebAssembly code, and then eventually, if it has to, I don't know, print to the screen, it will communicate at some point to the kernel, and the browser and the JavaScript layer are in the middle of it. So is it possible to, we can do that, it works, but can we avoid the glue code? Can we avoid the browser and let WebAssembly communicate directly with the system? Well, if we provide, well, we could bind WebAssembly directly to, let's say, POSIX syscalls. So let it, I don't know, open a socket, open a file, write a file, and that would work. You can literally do that already if you want to embed a WebAssembly engine in your own program. But it comes with some limits and some problems. Basically, you're giving full privileges to your WebAssembly executable. So what's the use of that? So instead of doing that, we provide POSIX-like APIs that are capabilities-based. Capability-based means that basically you do not give full capabilities to your POSIX syscalls, but you are reducing the surface on which they connect upon. For instance, instead of open, you give them open at. So you can give your client a restricted view of your file system. So just open, for instance, a specific directory. Most operating systems nowadays, especially mobile operating systems, are doing that. You may notice, even on Mac OS, proper Mac OS, you sometimes have to give privilege to an application to open a specific directory instead of the whole file system. So instead of giving your evil executable here, the risky application, an entire view of your root file system, you just give it a view of a scoped part so that you limit the attack surface. And the same you can do for networking and everything else, which is basically what Docker does. I mean, what containers do. So you are running an executable, but you're giving it a limited surface, a limited visibility over your entire system and the resources. I took this from my colleagues, Adrian, at Oradev, his presentation, WebAssembly for the backend, which gives you a better comparison, one-to-one comparison between the JVM and WebAssembly runtimes. So JVM is skewed towards, it is biased towards the language, the Java language, while the interesting part of WebAssembly, for instance, is that it's biased towards hardware. There are specific instructions to leverage the capabilities of modern hardware. For instance, SIMD instructions, which are missing in the JVM, just to give you an example. While the JVM nowadays, the OpenJDK, is a multi-vendor effort, it is definitely driven by Oracle. There are multiple vendors contributing and working and driving efforts, but there's definitely a major contributor, which is Oracle, while WebAssembly is definitely multi-vendor work driven by W3C working group. Java, it's more used nowadays on the backend, and of course WebAssembly, it's a bit more biased towards the browser, but as we saw, as we're saying, you can use it also in the backend. If we have enough time, I'll show you a tiny demo. There are other languages that share the object model, GC standard library, but on WebAssembly nowadays, every language brings their own object model, GC standard lib. I don't think I can give a lot of depth on that, but if you have questions, just ask. So I'm going to give you just a brief overview of some runtimes that are available. On Docker, Docker is under the hood is using Wasm Edge, which is one of the runtimes that are available. There's Wasmer, which also brings a delivery platform, which was mentioned with Docker. WAPM is the analog for NPM for WebAssembly, through which you can download, push. Basically, it's Maven for WebAssembly, if you'd like, or NPM for WebAssembly. Wasm, which is the project I started to work on, which is a zero-dependency WebAssembly specifically meant for Go, because if you notice, I don't know if you noticed, but most of these runtimes are either C, C++, or Rust. There's nothing specifically meant for Go, and Go comes with a set of restrictions that makes it more convenient to have a WebAssembly runtime written in Go. Wasm is probably the most famous, and a lot of projects are using it. Envoy. So there are projects that are already using WebAssembly for extensibility purposes. So the runtimes that I showed were to run WebAssembly out of the browser to do standalone applications. Envoy is using it for doing plugins. Red Panda, the native Kafka alternative, compatible with Kafka, it's using WebAssembly to do filters in the core. This is interesting. The Z compiler is using WebAssembly to do the bootstrapping of the compiler. I won't go into the details of that, but it's awesome. Lunatic is an Erlang-inspired runtime for WebAssembly. Under the hood, it's using Wasm. Crustlet is to run WebAssembly payloads in your Kubernetes clusters. CRUN also has the possibility to run WebAssembly in your Kubernetes cluster. So there's a lot of interesting projects that allow you to run WebAssembly in a number of ways. Last thing that I want to show you, 1 minute. I want to show you this Fermion. It's another startup, it's another startup that's working with WebAssembly. They delivered this spin framework for doing web applications using WebAssembly. I'm going to do the demo. So this is my hello world type of program. As you can see, it takes an argument, and if there's at least an argument, it will say hello using that argument in the message. Otherwise, it will say word. So I can compile that to WebAssembly, and then I can run it through Wasm. So if I pass Voxed, it will say hello Voxed. Otherwise, it will say hello world. Now, what, you may ask yourself, why is it printing this content type? So there's an interesting bit of technology that is embedded already in Spin that's called Vacchi, and you can also download it as a standalone. The name Vacchi, the GI stand for the GI in CGI. If you recall that, basically you used to write web application by writing self-contained executables that read from the standard input, wrote to the standard output, then interacted with the environment variables. This is a very bare-bone way to write a program, a web application, and it came with a lot of downsides. Basically, the original, so not fast CGI, but the original mechanism working was that at every web request, you will spawn an executable. And that's a DDoS act vector denial of service waiting to happen. So, but it was really convenient. So what they did with WebAssembly is, let's say that we're using the same POSIX APIs to read from standard input and writing standard output and reading environment variable, but instead we embed those inside a safe execution environment. And instead of spawning a new executable every single time, we just instantiate the WebAssembly module. So by doing that, I can configure Spin, bind my executable to the hello route, and then I can just say spin up, and it will spin up very fast, of course, my executable at the hello endpoint, and then I can just say hello voxed, and it will print hello voxed. So this is really cool to me because basically it's showing that by even with the bare-bone set of APIs, bare-bone POSIX APIs, you can already do a lot of interesting stuff with WebAssembly. So things are moving fast, things are changing, but the ecosystem is moving forward with it. So yeah, I don't think we have enough time to talk about this, but there are a lot of different interesting projects that are trying to target WebAssembly through compiling Java or Java bytecode. Of course, Java J2CL compiles Java source code into JavaScript, but nowadays it's also starting to support WebAssembly, and there are others such as bytecoder, JWebAssembly, TVM. There's also a flavor of TVM that supports WASI to run outside the browser. There's ChirpJ, which is a proprietary technology, but it's impressive because it really supports running Swing applications in the browser without Java applets. There is even Chrome extensions to run Java applets without recompiling using directly the runtime. By the way, it's a London-based startup. I don't know them personally, but they're all Italian guys if you're interested. Impressive demo. Running x86 binary directly in the browser through their compiler toolchain that also compiles C, C++. Impressive work. We mentioned already Git. Kotlin is starting to support WebAssembly and also WASI. Back to browser, honorable mention. Doppio JVM, it's a JVM that runs in your browser and interprets bytecode written in JavaScript. I wanted to also mention GraalVM because they recently targeted RISC-V through LLVM, and so they just mentioned, in a note inside the article that presented the feature, that possibly at some point they may support through the native image toolchain to target WebAssembly. Wasm on Java, so the reverse. I want to run WebAssembly inside your my Java JVM. There's a number of projects. Everything is in flux. Definitely, probably the most advanced must be the GraalVM based. But there are other. My favorite, Happy New Moon with Report, because it's a very silly name. And well, there's a number of limitations, because a lot of these proposals are still in progress. For instance, most people mention garbage collection, but the one that scares me the most, well, the one that worries me the most, it's exception handling, which you can support, but you have to generate a lot of code. And so there's a lot of work to do to support proper Java, including supporting threads and atomics outside the browser. Right now, in the browser is able to run to some extent that, but it's emulating through WebWorks, so it's not equivalent. Anyway, That was it. Thank you for staying with me today, and I hope you enjoyed your session.